I kind of work a bit on noise in a particular way, and a particular definition of noise, and I'll try and go through that. But to give you a background, I'm not going to go into what I do, but all my work is essentially about inference. So how do we make inferences about the world? How do we perceive things, or how do we come to some kind of idea about what we think about the world? And I work on observing actions and how we execute actions. So my work is on how you know that this person is throwing rather than catching this particular object. So these are the kind of questions that I'm interested in. And I'm not going to talk anything about that today, but what I'm going to talk about is the framework that we developed in collaboration with Carl Friston, and it's Carl Friston's ideas, about how the brain might try and implement this, and what kind of things it says about how we sample the world, and what are the key parameters required to make accurate inferences about the world. So the problem in any form of inference is that you have some form of input that's coming in, some form of inputs coming in through your senses, and what we want to try and do is trying to make a guess at what we think the cause of that input is. And most models that you will come across will basically kind of assume that we can just read off the cause from the input that comes in. So this is a very simple model, which is called, all these families of models are called recognition models, and this is the most simplest form of a recognition model. And what it assumes is a particular feature. It's a perfectly valid recognition model, but it assumes a one-to-one mapping between the input and its cause. And so, if we have to make a response to a cause, we might have to have a one-to-one mapping between what we see and then what we do. So a quite classic example of how this can exist is if you're used to driving and you see a red light come on, you may have a reflex to put your foot down on the brake, because in general you've learned an association that's direct and one-to-one between red lights and braking. And the majority of people who do behavioural work would employ something similar to this to get people to respond. So generally you have a response to a particular type of stimulus. So this is a perfectly good type of model. However, the world is not really like that. So basically all this is schematic, this is not data, just to point out, in case people thought I had weird data. So really the world's not like this, and we have many different forms in which we can see the same thing that can be caused by lots of different things. So because of the fact I work in the motor system, we often say things like, if you see someone by the side of the road waving their arm like this, you have no idea what on earth they're doing. They could be trying to hail a taxi, there could be a fly buzzing around their head, they could be vigorously trying to get the attention of someone on the other side of the street. So basically from the input alone, there are multiple different causes, and if you're trying to infer what you think they're trying to do, then that becomes an impossible problem. You can't do it just by reading off the input. So I hope that's clear from the schematic. So those two slides are going to repeat a lot, but fortunately they're very simple. Importantly, from what I'll say at the end, and because this is about development, at the moment, we don't know what these models are. So how we get from the input to the cause. And we're assuming that these have been learned during our lifetimes. So one cause of any form of failure in being able to correctly infer a cause from what you can sense could be caused by some deficit in how these are learned during development. Okay, so to give you an example of how this can occur, I hope you can read this. Can everyone read that? Okay, so that says Jack and Jill went up the hill. Or you could have, in the event of a fire, please leave the building. So this is an example given by Chris Frith and Carl Friston in their paper. So here, the students you might notice this is actually exactly the same word. So your sensory input is exactly the same, but given the context in which you see it, you may have read it as being a different word from that which you see. So in the two different situations, you may have read this as being went or event, depending on how it occurred. And I'm sure you can think within your everyday life of situations in which you get these situations in which the same thing can occur by the same sensory input can mean two different things. So really, as I was saying, what I work on is how we're basically able to make something with inference. And really, everyone's familiar with a t-test and how you make an inference. So if you take a sample of what it is you're measuring and test whether it's different from something else. Now this has two key parameters. It has the parameter of what your mean is, but it also has this parameter of how noisy your sampling is of that particular, the thing you're measuring. So this brings us to the idea of the importance of noise or variance in what you're measuring. And Steve, his last talk, gave lots of examples of different sources of that noise. And I'm not going to talk about noise in the stimulus, but noise that happens internally. And in particular, I'll talk about how you may get a pathology in reading that particular types of noise. Now, for those of us who prefer Bayesian things, then you have two different sources of noise that can enter. So you have some estimate of what's happening in the outside of the world, your senses, which has a mean and a distribution. But you also start off with what you think is happening in the world, and that also has a mean and a distribution. And then you integrate those two things to give you your posterior probability. So this gives you two sources of variance. You have a signal variance, which can change. So if you basically think your sampling is very, very good, then your posterior will move closer to the thing that you're sampling. However, alternatively, if you have lots of noise in the system, you can shift in between whether you believe more your prior or more the sensory evidence that's coming in. Is that kind of roughly clear? Because that's kind of a fairly important feature of the rest of the talk. Is that you have two things that can basically change what you're going to infer. One is the noise on your prediction, and one is the noise on what it is that you're measuring. Now, in extreme, particularly with the prior, you can end up having what's known as a flat prior. This is where you have infinite noise. In other words, it's completely uninformative. It will tell you nothing about the stimulus you're coming in. So if you have a totally noisy prior, then you won't add anything to your inferential process. It will just be redundant. So this is the model that Carl's put up of how the brain does all this. And it looks far more complicated than it actually is, or at least it looks far more complicated than it is to describe. So really what it says is there's something in the world. So this is the brain, and this is the world. And when it says there's something that happens in the world that has a cause. So this is the truth, if you like. This is what's happening in the world. And given some change in that cause through some state equation, so for instance, if I was dropping a ball, my cause would be I've dropped a ball, but that ball will move, governed by some laws of physics, and these would be the state equations, and that will give rise to some sensation, something that's changing in the environment. And this is what I have access to. So this is what's coming into the brain, is this sensation. So I'm seeing this ball moving. And my job is to try and infer what I thought the cause was of that thing moving in the environment. I mean, it could be anything. I'm using moving just because it's naturally what I default to because of my research. Now, what the model, what this theoretical framework says you do, is that you start off with what you think is the most likely cause, given everything you know about the situation, and maybe what's happened preceding it in time. And given that, you can make some predictions about what you think the states are. And given that, you can make a prediction of what you think the sensory consequences of that cause would be. And then you can compare the two. You can compare what you predict with what you get. Now, if that happens to be completely true, and you manage to completely predict your input, then you end up inferring the cause. Because your guess was correct, so you will think that you know the cause of this. If not, then what this will generate is some form of prediction errors. And these prediction errors feed back to update both your predictions about the states and your predictions about the causes. Okay? So basically what you're trying to do is you have a model of the world inside your head, and that's what you're trying to do at any particular time, which is trying to model it. So the key bits here are basically what happens in these prediction error units. So it turns out that prediction error units within the framework have two terms. One is, if you like, the simple linear subtraction of what you predict over what is actually present. And that's shown here. But they're weighted by this pi term. And the pi term is the precision term. Now what the precision term is telling you is what's your estimate of how good your prediction is about the means of these different things. So if you like, this is your estimate of the noise. Now, the model is agnostic as to the source of that noise. So this noise could be noise that is in the stimulus. What's your confidence that the stimulus is representing something that's a true thing, like in your coherent motion stimulus? It could be neural noise. The important part here is that the weighting of this precision determines the prediction error. So if you're more precise, or if you think you're more precise about something and you're wrong, that prediction error will be higher. Now, according to this theory, what all the brain is trying to do is minimise prediction error. It's minimising surprise about what you're sensing in the world. So therefore, this precision term becomes a very important term, because it's a way in which you can weight which bits of a system you are particularly interested in focusing on. So Carl Friston and Harriet Brown have published this as a model of attention. So for instance, when you attend to different parts of your space, the thing that you can change is the precision with which you want to weight different parts of your space. And then automatically, you're going to give that more weight in your minimisation scheme, and so you'll be paying more attention to it in kind of everyday stuff. So that's a rather simple model.
Can I just ask a point of clarification?
Yeah, sure.
How do you know you've made an error, given that all you've got is sensory input?
Because you'll get a prediction error between what you predict and what you have.
Well, how do you know what you have? Because isn't that coming also from sensory input?
Yeah. So this goes down as far as the first sensory area. So we're assuming that you have your sensory inputs to the brain is like your lower sensory areas. So this is a critical point, because the model here is going to argue that we rely heavily on feedback-ward connections. Now, because there's much more work done with vision, within the major of visual recognition, there's a lot of work done on bottom-up visual processing. Now, but that is at a low level. So if you go back to, well, I won't go back, but if you look at those one-to-one mappings, anything that is a one-to-one mapping does not require this complicated framework to do. So if you're basically trying to say, this is a straight line, that doesn't require a one-to-one mapping. It's a straight line, or it's not a straight line. That can all be done in lower visual areas. So this really kicks in at the point at which you have an ambiguity in between what it is you're trying to infer and what it is that that area, if you like, is receiving as its input. So the assumption is that the lower areas can work fairly well on a bottom-up one-to-one mapping. Okay, does that make sense? Does that kind of roughly answer your question? But that's the assumption of this framework. So the idea is that you have a network of these areas. So really what this is saying is that you have, as we said before, your lower visual areas, and then you have your higher areas. Now these are deliberately vague in this particular sense, but what it's saying is that higher order features that are hierarchically or topologically greater in terms of what their abstraction is of the stimulus, will be represented at higher cortical areas, or in different cortical areas. And these predictions will feed down sequentially. So in each particular area you have these prediction units and prediction error units. But the point is, this is a hierarchical organisation, it's not just two areas. But for the rest of it, I'm only going to assume there are two things. So this comes back to what I was just answering your question about, is that if you have this one-to-one mapping, then you can do everything, and the model only really kicks in when you have to try and do these complicated inferences, because you can't do it the other way. So the idea is that you can start off with a prior about where you think you ought to be. So for instance, if I know someone says, I'm going to go and hail a taxi, and then I see them waving their arm, I can have a very strong prior in a particular space of this cause, which will make me infer the correct thing, because I've been given the situation. Now people who one of the criticisms of this model is that how on earth do we know where to stick these priors? And this is where I always argue that experimental situations are appalling compared to real life. So there are lots of things that would happen that could be entirely a true explanation. So if I was going to go and pick up this bottle, if I go and pick up this bottle, you would all expect me to pick it up like this. Now if I suddenly picked it up like this, it becomes a very different action, and it becomes very arresting because it's a very unusual and unexpected action. But once I've picked it up, you can then make the inference of what you think I'm likely to do with it, which is generally quite violent. So for the purposes of the rest of this, and this gets even more hand-wavy, it's really what I want to consider is that basically you've got a load of stuff that's top-down, yes, I know that, and loads of stuff that's kind of low-level sensory input. So I'm only going to consider these two different things. And if you like, the thing the brain's trying to do is balance out how much weight you want to put on your predictions over how much weight do you want to stick on your inputs. And this is because the prediction error is weighted by precision. So now we have a mechanism by changing this precision of which bit of this we both want to look at. So for instance, we can put all the weight on our sensory input and ignore this kind of top-down model. And we can have a good estimate of how you want to, of our senses coming in. So one good example of this is this paper by Tim Behrens. I won't go into the details of it. Basically, he showed people two cards, a blue card and a green card, and one of those turned out to be correct. And they changed the probability of which card is going to be correct. In between 80% of the time it will be one and 20% of the time it will be the other one. The subjects have to learn that over the course of the experiment. They're also given reward values for getting the right card. The reward values are totally orthogonal to the task, the probability of getting the right card. What they did, though, is they changed how often this switch occurred. So basically, how stable is the environment? It can either change rapidly, or it can be very stable. And what they're interested in knowing is during periods in which it's stable, you're better off integrating over a longer period of time. So ignoring the trials in which you get it wrong. If you're in an unstable environment, you're better off being much more sensitive to switches in this. And they can show that, indeed, subjects do change between the two things. This is where you're trying to sample your environment and use the information that's coming back to integrate over how long a time period is this a stable feature. So alternatively, you could say, I'm going to put all my weight in my top-down model. And it turns out, which I won't go into, is that this is required for movement. So within this framework, in order to be able to move, you have to attenuate your sensory inputs, which is what happens if you record it. And you put all your weight on your top-down model of where you want to move to. So, as I say, I don't study this, but we don't know anything within this framework of what happens during development. And within the framework, this is the difference in between learning and influence. So everything that I work on, and everything that the majority of people who research this framework do, is look at how the system works during influence. And we assume that the network is already completely learned, and you're switching between different models that you've already learned through development. So learning, we know very little about. And that's because all these models that I spoke about before, and I said we don't know how they exist, we have to learn them. We have to learn different associations between things that happen in the environment and what causes them. But the key for me is that if you look at this hierarchical network, this doesn't just appear magically at one time point. And how you progress from these low-level features through to really high-level features is going to change over developmental time with any individual. So what this means is that if you have, say you have some pathology that affects your sampling of the world at a particular point in this network, it's going to be very hard for that network to have anything meaningful happen to it at a level above it. Because the system is just, the information coming down is just going to be swamped in this kind of flatter and flatter prior. Does that make some form of sense? So really what my interest in terms of a thought experiment is not really, is when in development different pathologies or different diseases occur, could tell us quite a lot about where in this hierarchy you really have a bit of an issue with things going wrong. So I'm starting to do some work, again, in adults with schizophrenia, trying to look at where things go wrong in these networks of schizophrenia, and there's some models that seem to fit with this. But the nice feature about this framework is that it makes predictions about how we infer, but also how we move. So I'm interested in trying to look at things that are historically thought of as cognitive disorders, and trying to marry up and trying to explain in the same framework essentially low-level movement disorders inside different diseases that seem to manifest themselves in terms of cognitive and motor disorders. So I should say that within these frameworks, what you might say is if you have a problem during a particular level of that hierarchy, things that are more complicated to explain require more levels of the hierarchy to explain them. So if you think of things that have one-to-one mappings that are complicated, the two things that always jump out at me as being very, very complicated are social interactions, are enormously complicated things to resolve, and I would say I'm very bad at resolving them. And language is another one that's a very, very complicated thing to resolve. So therefore, if you're going to look at these networks and say, well, things could go wrong, you might expect high-level features to be lost first before low-level features. In fact, you might expect that if something's gone wrong, you might be very good at doing some form of discrimination on low-level features compared to someone that has all the entire network, because they're not in those situations burdened by this other information coming down, although it's useful in other situations. Now, because I don't work in this field, these are the questions that I guess I'm interested in. Is that we can have different pathologies that can increase noise, so you can have a noisy signal, but you can also have pathologies that don't change the sensory sampling, but they actually change this precision parameter. You can have a pathology of the thing that's changing the precision or the synaptic gain of that input. And this, I believe, is actually a very rich environment to try and study, and we believe that so at the moment I'm studying how this affects Parkinson's disease, dystonia, and schizophrenia, all within the same framework of saying this is a pathology of precision. Which I think it seems to be an explanation that can address very disparate symptoms within the same patient. And this becomes very hand-wavy now, because it says like a bit of a get-out. As soon as you've got a hierarchy, and the brain is hierarchically and complex organised, then you can, even within one patient group, seem to explain lots of different symptoms by just saying, well, maybe it's just a different, subtly different part of the network that's gone wrong, but with the same underlying pathology and modulations of this synaptic gain. As I said, because it makes this link between disorders that are cognitive and disorders that are motor, we can perhaps try to look at how linked these two things are. And then try to look at how this thing is being modulated and how this affects the